So, can you hear me? Yes? Well, that's the end of the week and the end of the day, after some, let's say, dense lectures. So, well, I guess we are all tired. I am a bit tired as well. So, this is, I would say, where, I guess, the tentative in this kind of, for this lecture 3 is really a tentative. I don't know how much I will be able to go through all what I've been preparing for today's lecture, but let's try it. And so the beginning of this lecture and all what I will be talking about next is relies on this slide that I've shown, when was it, this morning. We will be discussing the so-called time binding regime. So where optical lattices are not like very shallow optical lattices, but where you have already a certain amplitude which is such that the energy bandwidth of this lowest energy band is much smaller than the gap from the lowest energy band to the first one. So this is the regime that we will be playing with. And so, of course, in this regime, the one thing which happens is that because of the lattice being relatively deep, particles have a tendency to localize at the lattice sites. Okay? And the issue is that so far what we have been using are block wave functions which are extended in position space. Okay, they are kind of, let's say, the natural extension to a lattice of this plane wave. So to describe what happens in this time binding regime, what we would like is to change basis in order to go to something which is looks more localized on the site of the optical lattice. And so this is why we will be introducing these Wannier functions with the aim of having wave functions, so which are localized on each lattice site. And so we will define them like this. Qx. How did I wrote the phi? So I don't remember how I wrote the block wave function this morning. Something with psi, I think. Psi nq. Did I wrote it this way? Yes. So this is the let's say the band index. And this Q is the quasi-moment. So this Wannier function is just a discrete Fourier transform of the block function. And what we will see in a second is that it is localized at the position xi. Well, so maybe I should also have told you that I'm considering this lattice this is x, and this is xj plus 1, xj plus 2, right? So I've labeled the position of the lattice sites with this. The good thing about those functions is that they are orthogonals. So they form a basis. And so we will play with them. So what do they look like? Well, you can you see? No? that will be a lot of back and forth. So from the block wave functions, you can calculate them numerically. So you have a few examples with different amplitude of the optical lattice. So 0, 1, 2, 4, 8, 16. And what you can see, of course, is that the larger the amplitude of the optical lattice, and the more localized these wave functions are. Well, one see that they are located at a given position of the lattice. So you have, each time you have two Vanier functions, which are represented. So one centered at 0 and one at -1, solid and dashed line. And of course, you see that if the lattice is really relatively small, this Vanier wave functions still carry the fact that you have some extended contribution of many lattice sites which are relatively large. Well, of course, in the large deep lattice limit, this is hardly the case. Okay, so you may already know this Vanier function, right? Okay, it's fine. So let's move on. So now the idea is we have these lattice sites. And let's say that I put lattice amplitude relatively large, like 8, 16. So the wave function, they are relatively localized. And now the first question I may ask is if I want to describe the system, how do the particle can move from one side to the other, if I want to look at, let's say, transport coherence properties. And so therefore, I would like to define some tunneling through the different lattice sites. And I will use the Vanier wave function. And especially what we will be doing is considering, so I have not yet put interactions, so non-interacting Hamiltonian. And what we want is to look at what is the contribution to this non-interacting Hamiltonian when you try to overlap to Vanier wave function. And so this is the way we will define the tunneling. So I can define a tunneling, let's say, between band n prime as a function of position x g prime as so the integral of the first Vanier function that will be located at position xj. Then I have this minus h bar over 2m gradient plus v, let's say the lattice of x, times Vanier function n prime x minus g prime. Okay, this is a general, let's say, tunneling that I can introduce. Of course, we will directly simplify very much this situation. So the first thing is we are interested in, let's say, physics in the low energy band. And as I said, we will place ourselves in this tight binding regime where we can forget, or at least we will assume we can forget excitations to higher energy bands. So we will only take n equal n primes equals 0. So only tunneling in the lowest energy band. Then, typically you see that if we start to be in the tight binding regime, you may distinguish that here there's a small non-zero value for this Vanier wave function. But if you now look at the second site away, well, at least on this scale, we cannot distinguish anything. So this, let's say, contribution to a distance at two sites is even further reduced. So we will also consider restrict ourselves to tunneling to adjacent site. Okay, which means that I will just consider J prime equals J plus 1. And so all in all, what I will be saying is that I will be looking so at this type of tunneling, next neighbor in the lowest energy band. So I just wanted to show you how it looks like making this, this approximation. So what you have here is plotted as a function of the energy, by an energy scale of recoil, of course, as a function of the amplitude of the optical lattice V naught, next neighbor, and then second side distance and third side distance. And so you see that these tunneling amplitudes are obviously very much reduced. And okay, if I neglect the two dash line, at least it's a first good approximation. Good. And so I will, did I, well, no. And so now I will write my Hamiltonian. Just in second quantization with, let's say, some operator that I will write AJ, dagger, which is to put a particle, create a particle in on the site J. So all the part of the Hamiltonian that was like kinetic energy and optical lattice, this will be governed by this tunneling energy term, right? If I consider a particle on site J plus 1 and site J, which means that my Hamiltonian will be written, I can write it this way, J times Aj plus 1, Aj, which means, well, I can even do something like this. J plus, well, now the J plus 1, it's not that, I mean, I have also J minus 1, so let's put it this way. J prime, so I remove a particle from J prime and move it by one side, and this is the, what means this brackets, it's just only the sum of the next nearest neighbor. Okay, so this is the non-interacting Hamiltonian. The one thing we can also do, because here as a potential energy I've only put the optical lattice, but you may imagine, and this is what we always have in practice, that you have, for instance, some other trapping, like a box, a harmonic trap or whatever. And so if you want to add an on-site energy, then you will just add a term of this kind, of course, Aj1, where, so this is on-site energy. So that if you want to add any trapping potential or whatever, then you have it. Okay.
David?
Yes?
Is there, when you put a minus here, is it because J00 is there's a minus over
What did I put? So I put a minus because of I know the final result in the sense that if the particles which are non-interacting, then I gain energy by having them delocalized. So this term should lower the energy, right?
That means V0, 0 is negative.
And yes, because they have opposite signs on adjacent sides. So you're right that what I should do is put a minus here. Thanks. Well, we can see it here, right? Okay. Fine. So this is the non-interacting Hamiltonian. Actually, I'm just realizing that there was something I wanted to tell you as well, which is just to have a link as well with what has been doing and considering Anna Maria Ray, which is let's go to the very deep optical lattice limit now. So I did not attend all the classes she gave, but from listening to her this morning, I've realized that maybe I should make this link. So I'm considering like very deep optical lattice. And if you have such a lattice, well, you remember the band structure flattens when the larger the amplitude of the lattice. So if you have a very deep lattice, the band starts to be relatively flat. Okay? And this should ring the bell in the sense that if there is a state where you have like a discrete type of energy level, it's the harmonic trap. And so if you have a deep lattice, we can try to do harmonic approximation. So typically we have a potential that I wrote V naught sine square of kx. And so around x equals 0, this is of course SER times k square x square. And so this I can write it. Well, first of all, I will define a frequency for a site associated to the harmonic approximation. Okay, so omega s means what is the trapping frequency in a single lattice site in the harmonic approximation. And you see that I can identify the two. So this is SER, so k square, it's ER times 2m over h bar square, x square. And so with that, I have omega s square, which is SER square divided by h bar square for and I have a factor 4. So this is 2 times square root s ER divided by h bar. So in the harmonic approximation, which of course is valid only in the deep lattice, then I have this frequency in each lattice site, omega s, and of course then the states, I can write them n plus 1/2 times this energy scale. And so this is the limit that was considered by Anna Maria Ray, with also the let's say harmonic oscillator length which is square root h bar over m omega s. Okay, so this was just to link with the states that she was considering. And so you can wonder how much this approximation of having an harmonic oscillator, which, by the way, of course, this means if I do the harmonic approximation, it means that I will consider the Gaussian ground state of this harmonic oscillator. Well, I can consider the Gaussian ground state as the shape of this wave function on this site. And so the first thing one can do is compare what is the true Vanier function to this harmonic solution. Okay, well, at s equals 5, it really differs. At 30, you see that there's already an extremely good overlap. But you should be careful about one thing, is that while the shape of the wave function kind of match, if, let's say, s is equal to 30, there is still quite of a difference for the tunneling amplitudes, because the shape of those two wave functions on adjacent lattice sites are rather different. And so here you have plotted, once again in log scale in energy. In dashed blue, it's what I've defined, the tunneling within the lowest energy band at one side difference. And this is the harmonic approximation. And so you see that there is always a difference, which can be like a factor 2 or 3 in the tunneling rate. And, well, they converge, but you really need to go to very, very deep optical lattices so that they converge. Okay. And so what Anna Mardiare has been discussing is these deep optical lattices for this clock and all the physics that she has been described. Okay, so that was just like to link the regime she has been considering with the one that I'm discussing. Okay? So I've already removed the non-interacting Hamiltonian, but I promise that today we will be discussing interactions. So what we want is to add interactions to this non-interacting Hamiltonian. And this is the second reason why the wave function, the Vanier function, will be relatively suited, is because we will consider on-site, well, local contact interactions. And of course, they happen on-site. So that's another reason why having localized wave function as a basis is good. And so this interacting Hamiltonian in the time-binding regime is the so-called Bose-Bart Hamiltonian. Okay, so contact interactions. So G delta R J minus J prime with G, which is 4 pi H bar AS over M. And so as it has been already used before by Misha, the interaction term writes as a function of the field operator psi dagger R psi R psi R. So this is my interaction term. And so what I want is to go to the Vanier basis. So I will write psi so I drop the the index of the lowest band. Okay, I'm considering only the lowest band. Let me use J instead of. And then I want to plug that into the interactions. And so this, I mean, of course, what you could do is to keep all the band indexes. And then here you may have interaction with like 4 different band indexes with maybe different. And you can also keep all the positions different. So you have like also these 4 different positions that you can consider. But first of all, so we said that we will restrict to lowest band. And we will also do another approximation, which is that we will also restrict to considering the contribution, which happens only on the same site. And this also happens to be an extremely good approximation when you are in the tight binding regime. Okay, so then what I will be left with would be G over 2 for the interaction. I will have a sum. So I have 4 times operators AJ, but as I said, I will take them all on the same site. So there's only one sum, AJ, AJ dagger, AJ, AJ. Okay? And then I have the integral, the special integral of the Vanier wave function, which, since I said I'm only lowest energy band and the same site, it's the same Vanier wave function. And it's to the 4th power. Can you read? Maybe not. Huh? No, this I cannot move. J over 2, the sum of A dagger, A times the integral of it's fine with I'm going fast, but I think you know how to do these things. Huh? And now we will define the energy scale U, which will be just what is proportional there. So it's G over 2 times the integral of the Vanier wave function. Okay? So this is the strength of the on-site interactions. And so now I can go back to the non-interacting Hamiltonian and to add this term. So I add minus J prime. So I have A dagger J, A, J prime, plus U yes, well, one thing. First one is that this, I will write it, so this is A dagger, AJ, AJ, A dagger, AJ, minus A dagger, AJ, AJ. So this is n square minus n on site J. Okay, and now I better define. So why did I put the 2 in the definition of U? I don't know. What we usually do is to keep here the 2, yes, U over 2, and then so I have nj minus nj square minus nj, okay, which is nj minus 1. And I have this on-site interaction, epsilon j, nj. So here, nj is the AJ dagger, AJ operator, right? It's the number of particles on site j. Good. And so this is what I want to discuss today. Yeah?
Could you define the time-binding regime approximately?
Well, so what I said,
In which S it is valid?
what I said was I gave s equal 5. But I mean, this is arbitrary, okay? I mean, because of course, the thing that you want, and it's continuous, is to avoid having too much excitation from the different bands. And so typically, if the energy width of the lowest band is much smaller than the gap, then this is almost, I mean, it's hardly possible to have those excitations. But of course, it's a continuous problem. So what I said is, well, let's take s equal 5.
And up to which S the Gross-Pitayevsky description with the effective mass is valid?
Well, once again, this is something which is continuous. Well, I would say, well, a few recoil. Well, now what I'm thinking is, it depends the quantity you will be looking at. Because, for instance, maybe I will have time to talk a little bit about, in an optical lattice, you can crank up a lot the effect of quantum fluctuations and therefore quantum depletion. And so you have like appearance of those effects, which are beyond the bare Gross-Pitayevsky, relatively fast. But at the same time, if you are just trying to say, well, I want to send a wave packet, and I'm not looking at those like rather tiny effects, and see how the wave packet propagates, I would say that up to a few recoil, you can also use Gross-Pitayevsky. But let's say if you start to be 4 or 5 recoil, then it starts to be strongly, I mean, too much strongly interacting. Okay, so do you all know this Hamiltonian already? Yes? Okay. So you all know that there are 2 regimes. If we do j equals 0, what do we get?
Split.
Yes. So if I do j equals 0, I only have interactions. Well, somehow I'm assuming epsilon j equals 0 as well, so I'm taking the homogeneous case. What I have is I will have typically atoms on all the sides in order to diminish, of course, interaction energy. And they will not move from one side to the other. And so this is the, let's say, Monte insulator regime. And so the wave function there, you can write it. So this kind of perfect Monte insulator, I mean perfect in the sense that I completely neglect tunneling. This will be just a product of Fock state in each site. No, how did I write it? AJ. AJ dagger to the number of atoms we have in each site. Okay. And so the other regime is the one that we have already discussed this morning, which is if I take u equals 0 and j different from 0, what I will have is a Bose-Einstein condensate. And so, of course, if you would plot as a function of u over j, you know that in a BEC, you have off-diagonal long-range order, which, of course, you don't have in an insulator. And so you have some off-diagonal long-range order that will go to 0 at some critical value. And so here you have the BEC side. And therefore, on the other side, you will have the MOT. So one feature, of course, of an insulator is that it is gapped. And of course, what will be the gap? The gap is to to move one atom from one side to the other in order to induce some transport. And this is typically an energy cost which is related to the on-site interaction because you are bringing the two particles together. So actually, you have a gap which opens that is proportional to the on-site interaction U. Good. So I've it's better if I switch off the light. I've summarized here the main properties that you most probably have already heard of. So this is the superfluid. So as we discussed, of course, you have long-range phase coherence. The state is a covariant state, so you have Poissonian number fluctuation. You don't have a gap. I mean, you have seen, like for instance, at let's say low interaction, you can even use Bogoliubov approximation. So you know what is the excitation spectrum, and you don't have a gap, and it's a compressible phase. Of course, you can squeeze it. On the other side, you much larger than J, so no phase coherence. You have these atoms which are pinned to each lattice site. No atom number fluctuation. I mean, we have written it. It's just a Fock state. So this is, of course, just in the limit U over J equal infinity, strictly speaking. But we have a gap, and it's not a compressible state. So this was first, of course, not discussed with bosons. It was discussed with fermions in solids by Neville Mott. And the reason came from the fact that in some experiments, people were finding to have insulators where band theory would have told that it should be a metal. Okay? And then it was, Mott came with the idea that actually you should consider interactions between the electrons, and that those interactions, because of what we have describing here, may localize the electronic wave function and give you an insulator, even though band theory would tell you that it's a metal. And so in something like in the 80s, there's this celebrated paper by Fisher and so on, where they, let's say, expose the fact that actually you should also have this type of transition from a metallic conductor state to an insulator with bosons. And so we also call this transition the Mott transition, even though it's not the context, so with bosons on a lattice, for which it was initially developed. Okay. So let me now describe the first experiment with cold atomic gases, which observed this transition from a superfluid to a Mott insulator. So this paper was published like 20 years ago now. And so before just entering the paper, I just want to stress that this paper is really fundamental in our community because it was really the first time. So there was these ideas in the late 90s and then some theoretical proposal to actually realize this type of transition with an optical lattice and ultra-cold atoms. But you have ideas in the air. It's very different from actually looking at it in the experiment and getting it for real in the experiment. And from this type of paper, and along maybe we can cite a few other ones in different contexts, the idea of simulating with an experiment, realizing some toy models inspired initially by condensed matter, such as like this Hubbard type of Hamiltonian, could really be implemented in the lab and could really be tested and we could play with. So this is really one of the landmark papers that we have in our field. So what did they do? Well, so they put bosons in a 3D optical lattice. It was rubidium at that time. And so first of all, they looked at time of flight distributions. So I've already shown you these first pictures where, so this is without a lattice, this first one A. And then here you are in the superfluid regime where we discussed this morning the fact that you have peaks which are diffracted and that are, let's say, demonstrating the fact that your gas is phase coherent. So now, if you keep increasing the amplitude of the lattice, and so go towards the Monte insulating phase, this is the type of picture that they got, where at the end you completely lose phase coherence. You don't see that you have a lattice structure anymore in this density. The important point, because of course if you will have a thermal gas which is rather heated, you will basically observe exactly the same type of distribution. So the important point is that they also shown that they can start, so they load the BEC, increase the lattice amplitude, they go towards the Monte insulator. And, well, maybe one thing that I not said, I'm just realizing it, is that if you increase the lattice amplitude, you diminish the tunneling, J. Okay? And at the same time, you are squeezing the wave function, and so you are increasing the on-site interaction. So when you are, sorry for that was some kind of a basic comment I should have first said. If I plot the tunneling as a function of S, it goes down, and the on-site interaction as a function of U, it goes up. And so, of course, if you plot as a function of S, U over J, this strongly goes up with the amplitude of the lattice. So the way you can change this ratio U over J to go from one regime to the other is to tune the amplitude of the optical lattice, which is really easier. You just increase the intensity in your experiment, which is, by the way, very much different from solid-state physics. For instance, I was in a conference like two weeks ago where this guy was telling, so he's working with some special metallic structure which are kind of weird, and I don't understand them. But the point was, so all his talk was about we can cross the mode transition in a controlled way, and the controlled way is you put your piece of metal between two diamonds, and then you squeeze as much as you can. So you go to very high pressures. And so doing that, you deform the lattice structure. And with that, you can change tunneling and interactions. Okay, just because you have squeezed a lot the crystalline. And so this was like, he was presenting this as a really cool result because you can, in the lab, have a knob to change somehow the regime of interaction to tunneling. And so I was thinking, well, we have just to increase the intensity of our laser. It's much, much simpler than going to very high pressures. They are making measurements which are much more refined and much more accurate than what we are doing. I will come back to that in a second. So it's not that we are much better. But for some things, it works. It's easier. So, OK. So going from here to there, it's about increasing the amplitude of the optical lattice. And so what you can do, what they did, is that once they are there, they go back. They decrease the amplitude of the optical lattice. And they were recovering exactly the same pictures. So it means that the process is not that of like heating up the gas and getting a thermal gas, because this is not a coherent process, and it would not correspond to just a unitary transformation, but you can go back and forth in a reversible way. So this is really important. Another features that they looked at, yes, is they measured some spectrum. So I'm not telling you exactly how they were measuring, but this is the type of spectrum they were measuring. So this is energy scale here horizontally, and this is the amount of excitation. So in the superfluid, they were observing some kind of, let's say, excitation as soon, basically, as they were trying to excite, while in the Monte insulator, they got something which needed a certain amount of energy. And so you have peak here, and actually, this peak more or less corresponds to the value of the on-site interaction energy U. And so this was a strong indication that, yes, this phase is, has no phase coherent, and it's also with a gap. Okay. So once again, this paper is really a landmark. But once I've said that, I mean, now we have spent 20 years of working in the lab, and we can think a little bit about what was the title of this paper. And so the title is Quantum Phase Transition from a Superfluid to Monte Insulator, blah, blah, blah. And what I would like to ask now is, well, after 20 years and this first experiment, what have we learned about this quantum phase transition? And especially since we want to simulate and realize in our lab some models and test them and basically complement with some new information what can be done in, let's say, in solid-state physics, for instance, well, we should be able to make some statement about what we measure, and maybe to be even a bit quantitative about what we have as an information on this phase transition. And as I will try to argue, we have worked a lot on this transition, but I'm not sure that we have learned many things about those three words, quantum phase transition. So now I would like to review a little bit what has been done, and then so put it into light. So of course, what is the first thing that you may ask about a quantum phase transition? What is the first thing that you would like to establish?
That it's a phase transition.
Critical exponent, this would be the first thing. Sorry? Well, don't you want to know where it is located first? No? I mean, then we can think about critical exponent and so on, but just where it is located. And when you see those data here, there's a smooth change. No way you can tell where the MOT has started and where the BEC has ended. No, we don't know that. So before talking about the experiment, I would like to actually build up on what was presented by Misha before, which is trying to tell you how one can, what kind of approach one can have, treating with a mean field approximation the order parameter to get a first estimate of theoretically what would be the phase transition. So I think it's these are techniques which are helpful to have, let's say, some idea about and to have seen them. Well, I'm not a theorist, so that will be just kind of sketchy, but it's nice to have an idea what it is. So the question is, before going to the experiment, how to theoretically determine where the transition is. And so what I will be doing, so I want to understand where is the transition point, and I will be doing so-called mean field decoupling approach. So maybe I should start by saying that I already know that by doing a mean field approach, I will not be accurate. Why? Because what we want to describe is a set of particles which is sitting on lattice sites, and they tunnel, and they interact. And there is no reason why I can like take one particle and average all the rest to some mean field term in terms of interaction and possibility to tunnel, right? It's clearly a strongly correlated system. I mean, if you want to move a particle, it depends a lot whether you have one there already or not. And it's not just like an average value of the density around, okay? So we have this in mind, and we know that we should better use like full numerics if we can, and actually for the Bose-Hubbard Hamiltonian it works. I will come to that later. But still, with such an approach, even though we know it will not be like the best thing to do, we can get some good intuition about the physics. Okay, so what does it mean? Well, typically what we want, it's as it was done in the previous talk, is to write write equation which are one-body equation. And to do that, we will be doing the following. We will consider operators which are an average value that could serve as an order parameter, plus some fluctuations. Okay, so for the moment I've not written anything weird, but what we'll be considering is the fact that all terms that would be second order in perturbation will be 0. Okay, and this is where I will, where I do the approximation. I will only keep terms which are linear in the fluctuation. So you remember that what was done before was to use, I already don't remember how, was it psi? No, it was delta, the order parameter. So instead of having some kind of dagger, psi, we kept some delta, psi, dagger, psi, right? You follow me? Okay, we will be doing exactly the same thing. And so this you can write it A minus times B minus B. And so what we have is that AB, the product AB, will be therefore, so AB is here. I will have A average B plus B average A minus AB. So this is the equivalent of the delta and delta star if I put AB equal. And this is, if I'm not wrong, this is the correction of the energy that Misha decided to drop. He just wrote it and did not keep it. Okay. So on what type of operator we will be doing that? Well, we will start from the BEC. And we will write the on-site operator as, so a mean plus some, how did I want, yeah, plus some fluctuations. And this mean, because I'm starting from the BEC, this is, let's say, coherent state. So I'm saying that on each of these sites, I will have a coherent state plus some fluctuations. And I will neglect everything that will be second order in the fluctuation. So, in our Hamiltonian, we have terms which are which are the kind A dagger J, AJ prime. This is for the tunneling. So I will write them A dagger J psi plus psi star AJ prime minus modulus square of psi square. Okay? So from this, I got that. And this is where the trick is, because then I can write a one-body Hamiltonian. Why? Because I can mix this term. I will also have a term of this kind when I do the sum, right? I'm talking about I'm describing this term. This one is it's the one in the Boson-Bart Hamiltonian that is non-on-site. Okay? So I'm doing this like mean field decoupling. And if I will have these two terms here, so this one I can write it as well. So it's AJ prime dagger psi plus AJ minus psi. And I can therefore put in the same, this guy with this guy, this guy with this guy, all the J prime together and all the J's together, in order then to write my Hamiltonian as a sum of simply on-site Hamiltonians. Okay? And so what will be these on-site Hamiltonians? Well, there's a part which is easy. It's the one we already know, the interaction term. Plus the on-site energy. And now I have those cross terms. So what will I have? Yes, so I have minus J. So I will have, you see, I have AJ dagger AJ here. AJ plus AJ psi. Okay? And this one, how many times do I have it? Well, I will have it the number of times I have neighbors. Okay? Because here I will sum with on all the next nearest neighbors. So this is times zeta, where this is a coordination number, which is just the number of next nearest neighbor. And then I have a plus zeta psi square. Okay? So you see that the trick is just about doing that. You neglect second order fluctuation, and so therefore you can separate the contributions and rewrite them as a simple on-site Hamiltonian. And so this is a sum of on-site Hamiltonian, so if you want to solve that, you just need to lower the energy for each site. And this is easy because you do it independently. Okay. So I hope, Misha, that I did not say anything wrong in deriving that. Yes? So I should have written, I don't know if I did, I have this term, and I have its complex conjugate. Or maybe I can... Well, this is the site label. Okay? So I'm saying that I have a site And this is the site number 2, this is number 3, 2, sorry, 1, 2, 3. It's getting late. Okay? And so when I calculate this type of tunneling, it's tunneling from site, let's say, 1 to 2, which is this term, or tunneling from site 2 to 1, which is this term. Okay? Yes? Yeah. Kind of. So then what I can do, so let's say that this I call it mean field. I can calculate what is the average of this mean field energy. And what I will get is some constant plus terms which are even power of the modular square of psi, this coherent state. And so there I have two situations. So if I plot this energy, I have a situation where A is positive, and I will have typically something of this kind as a parabola. And I have a situation when A is negative, and I will get this type of energy dependence with the other parameter. And what I can do then, so of course, I mean, changing from here to there, you see that I change the value of the other parameter. I mean, if I am in the blue, value is 0. So I have no coherent fraction. I have no BEC. While if I have in the orange, I have a finite value here, which corresponds to being in the superfluid regime. Okay? And so now what I need to do is to evaluate what is the value of A. So you can do that numerically. And what you find, so you find that U over zeta times J is 5.83 if you have n equal 1 atom per site. So this is the mean field prediction you get from such an approach. So I didn't know that it would be, I mean, such an approach was used in the previous class. And the reason why I'm just done that is that it's nice to have seen it because you use it in many cases. So these are two examples. Okay, so now we have one prediction, which is a mean field one. But as I said at the beginning, we know that it's not going to be really exact. So let's compare to real numerics. And for that, you can solve the Bose-Hubbard Hamiltonian in 2D and 3D with quantum Monte Carlo approaches, and in 1D with DMRG approaches. And so these are the results. So the mean field, I've plotted it, so you just need to use this coordination number, and you get those values. So for 1D, 2D, and 3D. And you have in front the corresponding numerical result. Well, exact, it's between quote. I mean, up to our let's say numerical errors. Well, you see that in 3D it's not that bad, right? The ratio U over J. This is 35 of mean field. It's 30 for QMC, so it's not that bad. In 2D, it starts to be a little bit less good, and in 1D it's really bad. So the reason is that in lower dimension you have exaltation of quantum fluctuations, and so you know, I said I would neglect the delta A, delta B, but in the lower the dimension is, the worse is this approximation. The other thing you see that we are always overestimating, and this is because, I mean, we start from the BEC and do this mean field approach from the BEC, and we therefore overestimate up to which value this coherent state exists. But okay, so these are the numbers. And I will like to tell you that there are some other approaches. For instance, this to truncate the Hilbert space to 3 states. So what you do, so this is my site, and let's say that I have 3 atoms in this site, on average. And so what I will be considering is the case where I have 2 atoms and the case where I have 4 atoms. So +1 and -1 with respect to the average. And you see that this also allows you, on top of the average number of atoms per site, to have some fluctuations, right? So it's kind of analogous. So it's not, you don't derive the things the same way, but it's kind of the same approaches. So get a bit of fluctuation and see what is the effect. So if you do that, you can obtain this formula here, where you see that you have U, J, and the coordination number zeta, on top of N naught, which is the average number per site. And this allows you to build such, let's say, kind of phase diagram. You have here U over J. Here you have the number of atoms per site, vertically. And this is, let's say, chemical potential. It's a way to change the total atom number. And what you see, so this formula here denotes the limitation between the superfluid and the MOT. And so this formula here, it's this dark black line here. And within this lobe, you see that the density is flat, equal to 1. So this is where you have a MOT insulator with N equal 1 atom per site. Here it's a MOT insulator with N equal 2 atom per site. Here with 3 atom per site. Okay? And everywhere else, it's a superfluid. So there is this notes by Fabrice Gerbier on his website, where this type of approaches is well developed, and it's really easy to read, so you can have a look to know a little bit more. Okay, so what time is it? 6? No, it's almost 7. Whew. So let's hurry up a little bit. So this approach also is well suited for the MOT, right? Because for the MOT, you typically, if you start deep in the MOT, you really have an atom number per lattice site which is fixed. And then if you want to know what are the quasi-particles on top of the perfect MOT state, then you typically need to move one atom around. So you will have one site with +1 and one site with -1. And these are, let's say, particle Hall type of excitations. And I just wanted to show you that this, with the quantum gas microscope I've been discussing this morning. So this is a MOT insulator with almost flat density. And on top of that, you see that you have these defects here on 2 sites. So what is it? It's a particle Hall excitation. You have 0 atom on one site, and the next one, you have 2 atoms. But I remind you that since you have light-assisted collision, you only do a parity projection. So if you have 0 and 2, what you see is 2 holes next by. And so this is deep. You see J over U is very small, so it's deep in the MOT. And when you start approaching, going towards the superfluid, you see a proliferation of these particle Hall excitations. And so this is also something that you can describe with this truncated Hilbert space with only 3 states. It actually works in first approximation relatively nicely. So it's nice that we can also see directly those particle Hall excitations of the MOT in the lab. Okay, so now, what have we done? I told you that we will try to say, look a little bit back. Well, we've observed the MOT transition in many different systems. So 1D, 2D, This is also 2D. I will come to 3D later. With different approaches, so Bragg spectroscopy and trying to measure the Conant's fraction. Or here, this is once again the quantum gas microscope, where what is plotted here is the atom number fluctuation. And so typically you see that if you are U over J very large, and you look at n equal 1 atom per lattice site, what you see is that the parity projection gives you as always 1, so close to 1. So it's indeed like the Mott thing. If you go towards the superfluid, you typically half of the time you have 0, and half of the time you have 1, because you have large number fluctuations. But all these type of measurements, they are not very precise in telling you where the transition is located. I mean, this type of experiment, which I can criticize because I'm the one who did it. You get this minima here. In blue, this is the expected value. But actually, this is cheated because it's plotted in terms of amplitude of the lattice, and U over J scales exponentially with this amplitude. So actually, it covers a large range of U over J values. Anyway, well, in all these things, it's no doubt we see the Mott transition, but the location is difficult. One of the funny things then is if you look at the literature, it's worse in the 3D case, where the mean field prediction should be actually even a bit more accurate, so the system is less correlated. So there are several experiments, and all of them, typically, they are compatible with the mean field prediction and not with the QMC calculation, which is, well, not expected. Recently in our lab, we have measured this transition in 3D, and what is illustrated here is that the transition, so this is the experimental region in red, we should cross the transition a little bit before 30, and this is where we actually see, it's 26, in recoil energy, and this matches well the QMC calculation. But this is cheating, in the sense that, well, yes, it does match well, but it strongly depends on what are the experimental parameters that you are using. So this is a phase diagram, finite temperature and U over J. So this is the superfluid here, this is the Mott insulator there. And this dashed line is supposed to be the superfluid to Mott transition in a homogeneous 3D system. Red tells you where you have, for our experimental parameter, a Conant's fraction, a superfluid. You can really see that, so first of all, the superfluid extends where you expect to have a Mott insulator. So this is not really good. And then you see that the superfluid already also is not present where you expect to have a superfluid in a homogeneous system. So what we did, we in our experiment, we were working along this isotropic line here, and we crossed the transition for the experimental parameters where the transition for the homogeneous system is predicted. But this strongly, okay, we knew that, and we put ourselves in this situation. But this depends on the experimental parameter. So you're not saying something very universal about what the Mott transition and where it is located. So why that? What are the issues in the experiment? Well, the first one is because we have a trap. And you cannot neglect this trapping energy, which means that we change the density at each site, which amounts to changing the chemical potential of a homogeneous system. And so in the lab, in a trap, you are always going all along the line here, and you cross different phases. For instance, in this A panel here, you can have like a superfluid here, then you go to a Mott phase with n equal 1, a superfluid, Mott phase n equal 2, a superfluid, Mott phase n equal 3. While, of course, if you think about Conant's matter, and if you think about the model, the prediction that one can make are those for the homogeneous system. So you see that this is clearly the fact that we have several phases coexisting at once renders our work difficult. So this was actually really put forward with this Monte Carlo quantum calculation, which are performed as well in a trap. And this is a good thing of Bose-Bart. You can really solve this entire Bose-Bart Hamiltonian also with a trapping frequency. And once again, this is nicely observed with quantum gas microscopes. So what you have here from the B panel towards the right well, it's written, you increase the atom number. And so you see that at the beginning you have a shell with n equal 1 atom, which increases a bit in the trap. So I remind you, these are in situ measurement. But then if you keep increasing the atom number, you start seeing no atoms. And why is that? Because you have entered the phase with 2 atoms at the center of the trap. So this guy here. And once again, it's the parity projection, so it looks like 0 atom. Okay, so, well, we are working with optical lattices in a trap. So there is actually, the good question is why we don't do it in a box. It's not that easy experimentally to really have a lattice and kind of a box. But then there is also one big issue, which is related to the entropy. Because you start with, so maybe I can comment on that just. On this experiment, why do we have a superfluid here? Is because if you are working at very low entropy, on the side of your mod shell, you have a superfluid. If you go a little bit higher in entropy, this is not superfluid anymore, it's just a normal, because this is where you put all the entropy. In the mod state, perfect mod state, you have 1 atom per side, the entropy is 0. So actually, the trap, in practice, since we always start with a finite entropy system, and we load the lattice, the good thing is that it allows us to see the mod at the center of the trap easily, because all the entropy goes in the shell around the mod region. So it's actually not so bad to work with a trap for this reason. Okay, then there is another big issue. We are working at finite temperature. I remind you, quantum phase transition means phase transition at 0 temperature. So the mod transition really happens here. So this is phase diagram U over J and T over J in temperature, in units of J. And so the quantum phase transition happens here while all the experiments are down there. So what we observe actually in the experiment, it's a crossover. It's not a quantum phase transition. So this is the first point. The second point is, of course, what is the temperature? How to measure it? You may, I don't know if you have already been told during the classes, that if you would let a BEC with a thermal fraction in a harmonic trap, let it expand during time of flight, and you wait quite a long time, and you take a picture, then the density profile will have these two forms. Something which look parabolic, which is associated to the condensate with mean field interaction, so Thomas Fermi regime. And here you have this pedestal, which is typically like Bose function at finite temperature. And so if you fit, so I don't know if you can see, but there is a green fit on this data. If you fit those profile, then from these edges here, you can extract the temperature. And this is what is routinely done in experiment with a harmonic trap. Well, in a lattice, you cannot do that, especially in the tight binding regime, just because particles are too much correlated, and you cannot separate what is the thermal depletion from what is the quantum depletion. And so there is no analytical formula with which you can fit your data. So this is not possible. And so what you can do is fit your data with quantum Monte Carlo calculations, where in the quantum Monte Carlo calculation you have one fitting parameter, which is the temperature, which is the one you don't know. So this was first done in Emmanuel Bloch group in Garching back in 2010. And here you have, so in red it's the experimental data, so a measurement, a cut through this momentum distribution, time of flight distribution. Here it's experiment, here it's QMC calculation, and they were trying to match the curve and extract the corresponding temperature. So this is actually relatively good, and the way they, somehow if you wish, benchmark that, is the fact that now they could be able to look at, for a given value U over J, where is the transition from superfluid, BEC, to just a normal gas? Okay, because of course, if I fix U over J and I crank up temperature, at some point I get a thermal cloud. Okay, and so by measuring this for many different positions, they could extract where the condensed fraction, at which temperature the condensed fraction goes down, and so you have these experimental dots here, and you see that they are kind of not far from these theoretical predictions. And importantly, they see that this critical temperature goes down as you increase U over J, which was the type of phase diagram I was showing before. So this is one way, which is somehow limited in their experiment to the superfluid only. Then there is another way, which is one again quantum gas microscopes, which is extremely well suited for the MOT region. And why is it? It's because in the MOT, what we say is a perfect MOT. It's once again you have, let's say, one atom per lattice site. What happens is if I put a finite entropy, if I put some temperature in the system, well, what happens is that I may have 0 here and 2 here. I will have some defect. And so this is exactly what they can measure with quantum gas microscopes. And so from looking at these atom number fluctuations, which are shown here, then they could, from how this changes as a function of the distance to the center of the trap, extract what is the temperature. But of course, this works if all the defects which are created are due to temperature. And then you can estimate the temperature. But go to the superfluid regime. It's a coherent state. You have a lot, even at 0 temperature, a lot of atom number fluctuation per site. So this is not a technique, of course, that you can use to evaluate the temperature in the superfluid regime. So we came recently with our 3D detection in the momentum distribution. And I show you some data of momentum density as a function of momentum. So this is deep in the superfluid regime, U over J equals 5. So you see that it matches. And if we put a QMC data, we can extract the temperature. Okay? And you see that it matches relatively well. By the way, these quantum Monte Carlo calculations we are comparing with are done for the trap. So it does not account for the way we do the experiment, the time of flight, the way we reconstruct initial velocity, and so on. And this is on top of a critical value for the homogeneous system at t equals 0. And you see that we can nicely distinguish changes in temperatures which are relatively low. And so we could extend what was done before up to the MOT regime. And so we could measure temperature all along this phase diagram. And actually, an interesting point is that our experimental data kind of follow an isentropic line, 0.8 kb per particle, which is, this is the entropy of the initial Bose-Einstein condensate that we load in the lattice. So we start, before loading the lattice, we have a BEC with 5,000 atoms and this entropy per particle. Then we load the lattice, and we can load it at the position U over J we want in an isentropic way. So this is, I think, one of the, let's say, most accurate demonstration that one can do adiabatic loading. So this morning I talked a bit about how to quantify adiabatic loading. I think this is one of the most accurate one, even though you see that it's hard to be accurate because error bars are relatively large there. Okay? So it's, let's say, the best statement we can say. Actually, the large, how much larger the error bars, this is also an interesting topic. And we could show that everywhere in phase diagram, it saturates the Kramer-Rao bound. So I don't know if you're familiar with Fisher information and Kramer-Rao bound, but for those who know, I mean, it works fine, which basically tells our measurement gives us all the information which should be available. Okay. So now maybe I will. So it's 7:05. Do I start this or no? So what I was trying to tell you. What I was trying to tell you is what we have been done so far, trying to locate the transition point, is not that accurate. And actually, we know now why relatively well. It's because first of all, we are not studying the quantum phase transition, and we are in a trap. So finite temperature and trap, and this modifies the physics. Nevertheless, we can go to the next question, which is like critical parameters, or let's say non-trivial correlations and possibly entanglement. So this I would like to discuss now.
Sorry to interrupt you.
Sure, sure.
But the QMC cannot handle your lattice, your potential.
No, it does. It does include the potential.
So even with the included potential, it gives those results that you see on previous. Not the ones that showed the last, but the ones before.
What do you mean?
The bad predictions that you observed. Yeah.
The
Vi-
trap potential?
That next.
This thing?
Yeah.
Well, this calculation. So I did not say, but so this is typically the, let's say, Conant's fraction for the experimental parameters, including the trap. So it's exactly for the atom number we use, the trap frequency we have, the lattice we are using, wavelength, and so on. So it includes everything. The only thing that we do not measure in the experiment, well, this is a strong statement. It includes everything. We think that it includes all what we have thought of. The only thing that we do not measure in the experiment and that we cannot feed the calculation with is the temperature. Okay, and so this is why then we use those calculations to extract the temperature. So typically, like the fact that, what we've been doing in this experiment was to keep the total atom number constant. Okay, and the trapping frequency slightly changes because actually you have a contribution which is given by the Gaussian envelope of the beams that you use to create the optical lattice. So when you increase the intensity to have a deeper lattice, you also increase the trapping frequency. And so this is the reason why you have here not red, typically. It's because in this region, we have a filling factor which is a little bit less than 1. So if the atom number per site is less than 1, then the critical temperature goes down. And what we did is to choose the total atom number and keep it constant in order to be n equal 1 close to the critical point. So this is why then we can compare with the homogeneous system and why it compares well. Because we are working in this region with 1 atom per site. The one thing that QMC calculations are not able to do yet, at least, is to calculate correlations. So far, in the momentum, so in real space, yes. In momentum space, it's really a tough situation because if you want to look at, let's say, two-body correlation in momentum space, this is, let's say, a complex two-body density matrix in the real space. Right? It's, and so therefore you need to consider 4 particles. Well, the momentum density, it's the Fourier transform of the one-body density matrix. Okay? So you need to have 2 particles and then you calculate the one-body density matrix and take Fourier transform, you get the momentum density. If you want to get momentum correlations, you need the 2-body density matrix in the trap. So this actually has not been done, and this is something that one can already measure in the experiments. So this is like not a fully easy topic. It's 7:10, so maybe I should stop here. Yeah, because no, I mean, okay. So typically, what I wanted to talk about is to present a few experiments which have been done on this Bose-Bart Hamiltonian, where people have been trying to extract critical exponents, look at, let's say, some kind of correlations, and measure entanglement, or let's say at least a Rayleigh entropy. So, well, either I do this on Monday morning,
take questions, maybe.
and yes, let's stop here. Yeah.
Earlier you were mentioning light-assisted collisions. Do you have some intuitive explanation for how this works, that light enhances the collision rate and leads to atom loss?
Yes, well, you can. What you can think of is that you have one of the particles that absorbs a photon, and goes onto an excited state. Okay, and this one has a potential which accelerated. Let's say if it is the particle distance, you have you excite the particle there, and then it accelerates because of the interaction potential in the excited state, in the upper states. So you get some kind of let's say extra energy in the collision, if you wish, thanks to having gotten the energy from the photon initially. I don't know if it explains much. It's just like you change the internal state of the atom, at least even virtually if you want to think of, and therefore the interaction is in another channel with an atom which is excited. And this gives you a collision rate which is much higher.
So maybe you're going to explain this on Monday, but so I was wondering, do we have any idea of how the coherence is established against when we are in the, once we go from the Monte insulator to the superfluid? Because I can see no reason why in the Monte insulator the phases in every lattice side would not evolve independently. Right? That's also why you see the destruction of the interference pattern, but how does it re-establish the phase coherence going back to superfluid?
Thanks to particle Hall excitation.
Okay, do we have any idea how fast that happens? Like, is it been
So this has been, so we can, like for instance with the three-state model that I was telling, then you can what you can do is write the state as the perfect mode state, which is the Fock state, I said, plus some correction with having like two atoms on the same site. And then you can calculate what is the coherence, which is phase coherence, which is provided back by this term. So this is one way to kind of have a, let's say, simple analytics about it. And it actually, this works relatively good once you are deep in the mode. So you just build a small number of quasi-particles. This works well. And this has been studied in experiments as well. So how the both, let's say, kind of equilibrium-like you change U over J, and you study how some peak appear in the momentum distribution, and from that you can extract some coherence length. And then this has been also been done out of equilibrium. You start from the mode and you quench to the superfluid, and you look how like phase coherence or actually some other phenomena are also occurring. Yes.
Again, on these light-induced collisions, but does it change anything if you go into fermions?
No.
No, it's the same.
Yes. But there is one thing that people are doing now. I mean, actually, there's this one experiment in Garching when they are doing it with fermions, is that they use this superlattice and a magnetic gradient to be able to image when you have two fermions on the same site of different spins, to first separate them in a superlattice with putting a magnetic gradient, and then being able to image these two sites. So they now are able to have both atom number per site and spin also resolved. Yes?
The comparison between the momentum distribution and the quantum Monte Carlo, the experimental data, is it averaged over many runs?
Yes.
Okay, and so how can you be sure that the temperature of all the runs is identical?
Because we claim that our experiment is a quantum simulator, and so you press the button and it does any time the same thing. Is not your experiment like that?
Maybe there is I don't know,
No.
photon which will excite something.
I mean, that's a good question. I mean, it's a fair question. The way I would answer is to tell you that. Merci, Juliette. These error bars here quantitatively match what you would expect if you would have a perfect system in the following sense. So in the quantum Monte Carlo calculation, you do like perfect calculation. And what you can wonder is the following. I have, let's say, 5,000 atoms, And on each shot, I will be able to measure the momentum distribution in a given way. And of course, I have fluctuations associated to this, detecting 5,000 atoms. And what I can do is to build this so-called Fisher information, which is associated to the temperature and associated to the momentum space, which is nothing but telling, well, I'm trying to quantify. I want to estimate the temperature, so it's just parameter estimation. And I measure a quantity, momentum density. How good can I estimate this parameter, T, if I measure the momentum density? Okay, so this Fisher information tells you that. And this M here is the number of shots that you use. So if you wish, in this value here, which is like the smallest value you can expect if everything goes well, from a measurement with a finite number of atoms detected and a finite number of shots. So the fact that these error bars, they match this quantity all around means that we have nothing that changes much from shot to shot. Other comments? Okay, so I would just like to have, sorry Thomas, just a final word.
Okay, let me stand still.
And the final word is the following. So I said I would be a bit provocative, saying, well, what have we learned about quantum phase transition for mod bosons like over these 20 years? So there are some stuff I've not explained, which we have learned some things. But to a young audience, I would say that this is a positive thing, in the sense that there are many, many measurements that we need to do, especially to understand many-body correlation and entanglement in the vicinity of a phase transition. So I will show some example, but we have done very few things on this topic, while it is at the core of a many-body quantum phase transition. So there is plenty of things to do on this type of topic, and so hopefully some of you will be doing it. Thanks.